Okay, let's get started. Let's get started, everyone. Okay, good morning, everyone. I have a handout again, so just take some of these, hand them around. Take some of these, hand them around. Take some of these, hand them around. Take these and just hand them back. There should be enough for this side. Okay, cool. So I want to get started talking about, hey, come on. All right, I want to get started talking about compilers in detail now. So we spent last week sort of talking about OCaml, which is similar to what you might have seen in 130 if you programmed either in OCaml or Haskell in 130. We good? Okay. All right. Hey, come on. I want to start lecture. Like, this is, all right. Okay, so we spent last week reviewing OCaml, and which might have been similar to Haskell or other things you saw in 130. And I want to start diving into things we need to know for compilers to get compilers going. The handout that I have going around, the side I want you to be on first is the side with the little tree drawings and the little math expressions in the top left. I want to get at a particular point here. I said on the first day of class that one of the things we want to do first in this big, long pipeline of our compiler is go from, right, there's a bunch of stuff over further to the right in this picture. But the first thing we need to do is go from source, like a C program or a JavaScript program or a Java program, to what I was calling this tree representation. And I gave it this vocabulary word that it was an abstract syntax tree. And this arrow, this function that takes source code and turns it into a tree, had a name. This function was called parse. Parsing is just a general topic in computer science and usually means going from some serialized representation like a string or like a binary representation that was coming on the wire on the network, right? Some serialized data into some structured form, right? Into some data structure, like a list-like form or a tree-like form. That's usually what parse means. The input to parse in general is a string or some kind of raw data, and we're trying to recover structure. That's what parse does. This ends up requiring that we think about languages, right, programming languages, at these two levels, at their source level and then at how we represent them with these trees. And by thinking about those two things, we can sort of figure out what parse is supposed to do. So I'm going to use another word for what we call the source code of the language. I'm just so that we can distinguish it from abstract syntax, I'm going to call this, the concrete syntax. Concrete. Okay. So our first goal is to come up with this parse function that's going to take strings that are concrete syntax of a program and produce this tree-based representation. Now, we'll see why the tree-based representation is particularly useful when we start programming with it. But for now, I just want to set this as a goal. Okay. And so I want to talk a little bit about concrete syntax. I wanted to actually just talk a little bit about what syntax is. And one of the easiest ways to start talking about syntax is just to talk about algebra, right? Just to talk about like algebra and arithmetic. Because what's syntax? What the heck is syntax? What the heck is syntax? Does anyone have a definition of syntax? Yeah, what do you think? How you write stuff. Other definitions of syntax. Other definitions of syntax. How you write stuff. Yeah. Stuff with grammars and rules. Other definitions of syntax. Syntax. Yeah. How to make sense of a sequence of words, or how a sequence of words has meaning, right? Other meanings for syntax. I kind of like those. I'm going to start with I like the first one in particular, how you write stuff. And then we can go from there to more structured meanings of what it means to write stuff in different ways. Can we formalize that anymore? Okay, so how you write stuff. All right, so the examples that are on the handout are useful ones to start with. So here's how I might write a math expression. That represents taking the quantity of 5 minus 4 and adding that to 3. It's a math expression, algebra expression. Now, there's all sorts of notations in the world, all sorts of syntaxes in the world for writing math expressions. This isn't the only one. This is sort of the dominant one, the dominant sort of Western way of writing these expressions, but there's lots of ways of writing math expressions. So another fun way to write math expressions, this is called reverse Polish notation. You can write 3, 5, 4, minus, plus. 3, 5, 4, minus, plus. Yeah, reverse Polish notation is hard to read if you're not used to reading it. I'm sure it's very easy to read if you grew up this way, but I didn't grow up learning reverse Polish notation, so it takes me a little bit to read this line. But the way you read reverse Polish notation is you read until you find an operator. In this case, the first operator you'd see is minus. And then you look at the two things before that operator and apply the operator to them. So if we wanted to think about evaluating this reverse Polish notation expression here, we'd read until we find an operator, apply the operator to the two things before it, so then we'd have 3, 1, plus, and then we'd start over. We'd read until we find an operator, then we apply the operator to the things before it, and we end up getting 4. Okay, that's like the right answer, right? By following that process, we sort of got the same nesting behavior where we did the subtraction first, then did an addition. Cool. This is a different syntax for the same expression. Right? These sequences of characters mean the same thing. They mean the same thing. They're just written in a different order, and somehow we talk about ascribing meaning to the different order we wrote them in. Okay? So that's reverse Polish notation. And then the other one that I have on the handout that I gave you is prefix notation, prefix notations, parenthesized prefix notation, where we put an open parentheses before every operator. The operator is always right after an open parentheses, and then we write the arguments after the operator. Okay. Here we go. So that's open parentheses plus 3, and then we would evaluate this the same way we think about evaluating sort of in our typical sort of Western style infix notation of writing these operators, where we find the innermost set of parentheses, evaluate that, and then work our way out, right? So these are 3 different syntaxes for exactly the same expression, or exactly the same program, we could say, right? I mean, we could definitely write these kinds of things that do arithmetic in programs. And I drew the tree for you on a handout, but I'm going to draw it again here because it's useful to have on the screen, right? This can be nicely represented as a tree of operations, where the root operation is a plus, its left-hand child is the number 3, and its right-hand child is a minus operation that subtracts 4 from 5. And all 3 of those concrete syntaxes, right, we could think of these as strings of text. Right. All 3 of those, we might decide mean this calculation, right, mean this nested calculation. And it would be reasonable to say that there's 3 different parse functions that might be able to take strings in each of these forms, right, parse 1, parse 2, and parse 3, and produce a tree that looks like this. Now, we might pick different ways of representing this tree in code. If you were at discussion on Friday, you saw this, but just to write it so it's on the screen, right, one way we might want to represent this in code is by saying an arithmetic expression is either a number that's an int, or it's some it does some operation where the operation is a string. That's going to be like plus or minus, whatever string represents that operation. And it's going to have a left-hand side expression and a right-hand side expression. So the way we'll represent expressions is by saying they're either numbers, that's like the 3, 4, and 5 in this tree, or there's some operator, and we represent the operator with a string, like plus or minus, and then they have expressions on the left and right-hand sides. So that's actually like a binary tree that represents these expressions. Binary tree that represents these expressions. What would be how would I use these constructors that I wrote to describe this tree example? What would it look like to use these constructors to like build this tree example that I have in the middle as a single element of data in OCaml? Right? How would I use these constructors? Try and write that down. Try and write that down. Write down sort of here, maybe on your sheet next to these things, right? Using these constructors, right? So you could imagine you could write, I want this expression to be, and write the OCaml expression here that uses these constructors to build that tree. The OCaml expression here uses these constructors to build that tree. Do that for a minute. Do that for a minute. Okay, suggestions. Somebody get me started on what I should write here. Yeah. So it's going to be an op, and there's going to be some stuff inside the op. What's the first field of the op going to be? Yeah. It's going to be number. Disagreement. String, number, string. So the first argument, we're definitely going to use number. But the first argument to op is which operation to do. And then sort of the first argument to that operation is a number, right? But if we want to write this out, the way we'd need to match this type in OCaml, right, we're going to write a plus for that, the first string here, because this is representing an addition. Then we can say that the first operand, right, the first expression here is the number 3. And then the right-hand side is, what's the right-hand side going to be? This other op, right? So then the right-hand side is this other op where we're subtracting num5 from 4, right? No? Ah, num4, right? From num4. Okay? This now is very clearly a piece of data in OCaml that can represent that tree. Okay? And now we could talk about writing functions that manipulate exprs, right? That like evaluate exprs down to values or compile exprs. That's now something we could do next, right? And it's going to be useful to have these tree shapes to do that. I want to pause here and make a point. It's not just these math expressions that we could do this for. The other example that's on the handout, just to be clear about how flexible this idea of thinking about different concrete syntaxes is. Oops, I'm going to move this other thing I was going to say down. I want to talk about that, yeah. So the other example that I put on there, just so we could have it as a point of reference, is saying, well, the same argument applies. Oops. The same argument applies to things that look more like traditional computer science functions, not just arithmetic expressions, right? This is like how we would write a method or a function in C to do something like square an integer. And it would be totally reasonable to talk about writing this in a different way. Maybe the way C decided to have its syntax defined is that it uses sort of this parenthesized form. And it says return. So sort of everything is like parentheses prefixes here. And we can see that these two ways of writing this, right, these two different syntaxes, I mean, they have the same structure. I'm not going to draw out the whole tree because the tree is on a handout, but they have the same structure. They're both these function kind of declarations they have a return type, they have a name, they have an argument that has a type and a name, and then they have a function body that has some return keyword and then this multiplication expression. So we could imagine, again, writing a parse function for the top thing or a parse function for the bottom thing and producing some tree out of it, And a tree in this case is going to capture all the information that we have in a particular function. Now, what do you think just a little preview of how we might draw some of these things out. Let's say we tried to do, some other type that's going to capture this kind of thing where we have a function declaration. What kinds of things might we need as we try to build up this kind of expression? Right? Up top, we just had op and num as the two things that we could have. What do you think we'll need here? What are some ideas of kinds of expressions we'll have to use to represent this kind of square thing? If we want to sort of extend the analogy we started here. I might go in this type. Yeah. A variable? Yeah, there's all these uses of like n in here, right? Which is clearly some kind of use of a variable. So a kind of expression seems like we're going to have something like some sort of variable. What do you think it'll have for fields? Yeah, maybe a string to represent the name. Right? Maybe that some of these n's are represented by a variable string, a variable that stores the string name. Anything else? Anything else that we need here? Anything else? Yeah. Maybe some sort of way of representing a function, right? Like maybe more than, maybe even more than just the name, right? Like square is just sort of the name, but there's all this information about the function, like its return type, its argument types, and then this other thing that's its body. So maybe there's something like some sort of variant for functions. Maybe they have some sort of, well, who knows, maybe how they represent int. Maybe that's just a string for the return type. Maybe there's a string for the name. And then it seems like there's like arguments, right? So there's going to be something here to represent the arguments. And I'm not going to write out in all kinds of detail how we're going to do this because we will certainly get to this when we talk about functions in the compiler. But let's say this first string represents the return type. This second string represents the name. Now this clearly represents the arguments. What do you think the last thing, there's one more thing we need here. What kind of thing might we have as the last thing here to represent the function body? What type do you think we'll use? If we want to represent the function body. Hand? Oh, scratch. Okay. Yeah. Maybe expression 2, right? Maybe we're saying that inside the body of this function definition, well, what's going to be there? Well, it's going to be an expression in this language we're talking about. So this is another place where we might start talking about these recursively defined expression types. Right? Yeah. Maybe even a list of expressions, right? Because we might have multiple statements or maybe some like block expression type, right? So we might need to refine it more. But there's going to be expression-like stuff in the body. Yep. Okay. So this isn't actually fully how we're going to represent function definitions. We'll get there in a few weeks. But it gets at the idea that we're going to have some interesting structured type all the way over here on the right-hand side that represents our programs. And somehow, we want to talk about what concrete syntax we have and how to get from here to there. Okay? And the how we get from here to there is going to be what we call our parser. Now, there's a lot of interesting design decisions to make when we choose a concrete syntax for a programming language. Let me say that again. There's a lot of interesting design decisions that we could make when choosing a concrete syntax for a programming language. What's your favorite concrete syntax for a programming language? What programming languages do you have that you like their syntax? You don't like any of them? Yeah. Python is often wins polls on what your favorite syntax is. right? Python has like this syntax that involves very few curly braces compared to C and Java, not so many curly braces. It's sensitive to indentation. Yeah, other concrete syntaxes you like or don't like. Other concrete syntaxes you like or don't like. Yeah. Really hate MATLAB, really hate MATLAB. What's wrong with MATLAB? What do you not like about it? There might be lots of things to not like. Oh, the index starts with 1. The index starts with 1. That's interesting. It's also interesting to think if that's a syntax problem or a language semantics problem, right? Because somehow the definition of what a matrix is in MATLAB is defined sort of by its runtime data structures, and it's decided on 1. Yeah. Other syntaxes you like or don't like? Yeah. Uh-huh. So the keywords there's badly chosen keywords that don't match what they actually do. Is that, yeah, so maybe there's badly chosen keywords. Other concrete syntaxes you like or don't like? Yeah. Bash is really annoying to program in. Yeah, I always have trouble in Bash. There's like a different meaning for single square brackets and double square brackets that has something to do with inserting security vulnerabilities into your shell scripts. Yeah, yeah, I don't know. Bash is really weird. Yeah. Other syntaxes you like or don't like? What's that? Lisp. You like it. Lisp, you like it. We'll talk about that. Actually, I'm going to make a historical note in a minute. So there's this idea, there's this programming language called Lisp. I'm going to make a historical note about it in a minute. So there's lots of decisions we could make. This is actually, I think, a bit of an understudied area of programming language and compiler design. What makes for a good concrete syntax? I don't actually know the answer. I have a few sort of informed opinions and some anecdotal data, but I don't actually know what makes a good concrete syntax. In part, you have to decide who your audience is, right? Is your audience like high school students? Is your audience general programmers, right? I don't know what makes a good concrete syntax. There's also lots of interesting design and work that goes into making a particular concrete syntax be parsable. A lot of work that goes into making a particular concrete syntax be parsable. To write this function that's going to take in this string and produce an instance of this data type. Right? There's different amounts of work that go in depending on how you define the concrete syntax. Okay? So I want to say, I think this is a fascinating, important, understudied, well, the how is very well studied, but the design is understudied. So I think this is an important problem. It's worth knowing a little bit about how to do this. It's also the topic in compilers that has the best, like, already written, already known solutions for the how of how to get from one of these input programs to a data type once you've made the decision about how what you want the concrete syntax to look like. And it's not something that I want to spend a lot of time on in this course. I mentioned this on the first day. I think of this as a back-end compilers course. This course really starts with these trees of expressions, and then we talk about everything that's interesting once we have these trees of expressions. There's plenty to say about how to write good parsing functions. If we did it, we wouldn't have time to talk about other important stuff. So we are going to make a simplifying assumption about syntax. We are going to pick this kind of syntax. Pick this kind of syntax for this course. We're going to pick this kind of syntax because it is really, really unambiguous what's going on in these parenthesized prefix operation expressions. Really unambiguous what's going on. We don't have any decisions, like I can't even write really an expression in this prefix syntax where we get into an argument about operator precedence, right? So, like operator precedence, what do I mean by that? Well, in like C or Java, we could write programs like n times m is greater than x. And we have to know, right? All of you know, like you have this in your bones from writing programs, that this will multiply n times n and then compare it to x, right? All of you know that, right? I could even reorder it and say n is greater than m times x. And you still know that this is going to multiply m times x and then compare it to n, right? You like have that in your bones as programmers. And it turns out to tell a parsing algorithm that greater than is actually lower precedence, right? We should always do the multiplication first. It's well known how to do it, but we'd have to go through so much algorithmics of parsing to make it clear why we can make that work that we'd be like in week 3 or 4 before we started talking about interesting things in the back end of a compiler. Okay? So I don't want to get into this entire discussion of how to handle things like operator precedence, how to handle things like different kinds of indentation and matching curly braces. So we're going to pick this very simple representation where everything is unambiguously parenthesized with the operations that matter coming right after the open parentheses. Okay? So we're going to pick this. This has a name. This is a well-known historical format for writing not just programs, but for writing data. It's like a serialization format for writing programs and data. And its name is, it's called S-expressions, is the name of this format. So, oops, let me just scroll up so I have the example on here. Okay. So this is called S-expressions. And the idea does come, someone mentioned this, the idea does come from a programming language called Lisp. This is an old idea from the 60s. And the idea is that every S-expression is either some atom, they call them, some just string or number or operand, some basic string, or it's a list of other S-expressions. So every S-expression is either an atom, things like int or square or n in that example, or it's a list of other S-expressions. And the list is some parentheses around the list of sub-S-expressions. And many programming languages, including OCaml, come with a built-in function that can take strings and give you back an S-expression for the string. So just sort of a default library function that's often provided. And this is what we're going to use to represent the concrete syntax of the programs we compile. So let's talk about a few examples of this. Here's the type that we're going to use in OCaml to represent S-expressions. We're going to, there's a function called ofstring that will provide you. That's just a standard OCaml library function that takes strings and produces instances of this type. Okay, so let's go back to one of our earlier examples. Let's go back to the arithmetic example of doing plus 3 minus 5, 4. Okay. And I want to think about this as a string. Let's think about this as a string. Because now what we're going to imagine is, let's just say our programming language is going to take in strings that look like that, and that's what we're going to compile. So the first step we need to do is to parse these things. Okay? So if we want to treat them as S-expressions, we're going to assume they're S-expressions. We're going to use a function like this ofstring function that consumes this string and produces an S-expression out of it. Okay? So well, again, we might say next. Let me just write this as an actual call so it's clear what we mean. Of string applied to this string. Okay. What do we expect that to produce? If our representation of S-expressions is this type SEXP here, what do we expect this to produce as an answer using those constructors? Take a minute, think about this. What do you expect to see come out here using this SEXP type, using the constructors atom and list? What do you expect to come out for calling ofstring on this string? Take a minute, talk about it, talk to the person next to you to iron out any confusions you have, and try this out. Okay? What do you think is going to go here? Just think about this SX type, right? So what do you think, like the thing to think about is, what do you think the very first constructor I'm going to write there is? An atom of a whole string? then SX wouldn't be very useful because there would be, ofstring wouldn't be very useful. So expect that ofstring does look at the parenthesized structure of this thing.
Okay.
Right? Yeah. So the question to ask, if you're sort of sitting here wondering where to start, is which one of those constructors, so there's this Atom constructor and there's this list constructor, based on the structure you see in that +3 expression, what constructor do you think goes first? Like what's the sort of outer constructor the first constructor will call?
The list?
Yeah, so it's going to be a list. So we'll have a list, and then we'll have some number of things in the list.
Yeah.
Right? What do you think the first thing in the list will be?
An atom?
An atom
Yeah.
of, what's the string going to be in the atom?
Oh, the parentheses? Or, no, I guess the plus?
Yeah, the plus,
Yeah.
right? So it's going to be this list where the first thing is an atom that's this plus.
Okay.
And then the second thing is going to be represent the 3, whatever 3 should do. And then the next thing is going to be whatever this -5,4 should do.
Okay.
Okay, all right. So some people, I'll go up that side the next time I ask a question and walk around. Sorry, I didn't get to you all over on that side. But I heard some good suggestions on this side. So one way to think about this is we're looking at this structure inside this string, this parenthesized structure in here. Someone said, well, look, we're giving it a string. We're just going to wrap atom around that string, right? That's the answer. That's the answer. So someone here, the suggestion was, well, this is just atom of, this thing, this whole thing, right? Just atom of that, right? And that, it would match the type of string, right? We could say that that's the right type. That wouldn't be looking at the structure inside this string. And so I want to be clear that the intent of ofstring and what ofstring actually does is it does look at the structure of this. It looks at the parenthesized structure of the expression and uses that to build this nested representation. Okay, so it's not just going to be an atom of this string. It will be a list containing something. It will be a list containing something. And, what it's going to be a list of is the stuff inside this outer set of parentheses. Right? So there's this outer set of parentheses that tells us, well, this is going to be a list of stuff. And the things in the list are going to be the sequence of things inside there. So the first thing inside the parentheses is, what's the first thing inside the parentheses? The plus. So we represent it like this. Atom plus. So everything in this list, because the type says SX list is going to be an atom of plus, right? We can't just use the raw string. Everything in this list is going to either be an atom or another list, another use of the list constructor. Okay. So, whoops, semicolon. So what's the next thing? What's the next thing that's going to go here? Atom 3. Any other suggestions? Atom 3. Okay. And it's going to be the string 3. Oops. Because atoms always take strings, so it's just breaking things up on these space and parentheses separated boundaries. And so then the next thing in the list, what's the next thing going to be after the atom 3? Another list. And this list is going to contain the minus, the 5, and the 4 all as atoms. Okay? So it's going to be atom of the minus sign, atom of the 5, and atom of the 4. So this is actually what you'll get, the helper function we provide on the next programming assignment. You'll actually get this kind of answer out from calling of string on these strings with these nested parenthesized expressions, or S expressions is the sort of vocabulary word for what they're called. Okay. Now, we had this nice type that we defined earlier for our expressions in this little language where we talked about having binary operators, right? Just to refresh our memory, it was this type. Or an op of string expr. And that's not that, right? Ofstring didn't finish parsing our program. If our goal was to write a parse function that takes in strings and produces expressions that we define, right? This is our expression type that we said is a useful way to represent this little language with addition and subtraction, right? That's what we said we wanted to get to from parse. We want to take in a string in the source or the concrete syntax and produce an expression in our abstract syntax, this abstract syntax we've defined. This did not get us all the way there. Right? This did not get us all the way there. Right? This Atom list SX type is not this type yet. Right? So, but it did give us some structure. Right? Before, all we had was a string. We had no idea if there were any nested expressions in it, how many operators were in it. We had no idea what the structure of the string was at the start. Now we at least know that there's this list Atom nested structure to it. Right? We found all the nested parentheses and got to this point. So we're sort of like, we're sort of halfway there with the S expression parser, right? We have the front half of parse, right? Parse for us in this class is really going to be these two steps, right? We're going to need to first, we'll use ofstring to get from the input string to an S expression. And then we're going to need to write a function that parses the S expression. And that's going to take an S expression, one of these things we just talked about, and produces an expression in the language that we are working on to compile, right? Because we'll have this useful data type expr, and that's going to define what we're going to take and compile. And this type's going to be useful because it has this nice structure that clearly looks like some kind of, at least for this little language, looks like some kind of binary tree. All that structure is going to help us write the compiler. So we need this last step of taking the S expression and producing an expression, and then we can use ofstring with this, and any string we can get the program for it. We can get the abstract syntax tree for it. Okay, so let's think about writing parse S expression a little bit. Let's just set up this parse S expression function. So parse SX is going to take in one of these S expressions. Any suggestions for how to start writing this? How to start writing this? Just let me get a let in front of it. Should I start writing this? Should I start? Suggestion? Match? Suggestion? Pattern match? Suggestions? Yeah, we have an instance of a data type as an argument. And in OCaml, similar to in Haskell, a really good way to start functions like that is to think about matching under different cases. We sort of have to match under different cases to figure this out. Okay. So we're going to match on S. And the two cases are going to be either it's an atom of some, I'm just going to call it stir so we can tell it apart from S, or it's a list of some elements. We'll do something in both of these cases. Yeah. Does that mean that every list will have exactly 3 elements? What's the that in your question? So if we're going to parse this kind of program, you mean the kind that has open parentheses, operator, and then the 2 operands. You're saying, does that mean it's always going to have 3 elements? So if all we have is binary operators, every good program, right, every program that we can actually like compile and run will have three things in each list, right? It had better, right? It had better. If it doesn't, then we're going to run into some issue. You're making an observation where you're saying, look, if elements isn't 3 long, what the heck are we going to construct for an expr? Right? That's kind of your argument. You're saying, if this list of elements isn't exactly 3 things long, where we can interpret the first thing as like a string operator, and then the second 2 things as expressions, then like what can we even do with that thing? Right? What can we possibly do with that list? Yeah, that's a really interesting question, actually, to look at this and say, well, is there anything more we could say than just being 3 length? Any more restrictions on it than just being length 3? Any other restrictions on what elements should be? So we made this observation that, at least for this language, if all we have is these binary operators, it had better be that elements is length 3 because it's going to have the operand, which is either plus or operator, which is either plus or minus, and then it's going to have some arguments to it, which are either numbers or nested expressions. Any other restrictions? Yeah. So the first element had better be an operator, right? It had better be an atom containing a string that represents an operator, right? And then the second and third thing, well, we know that they have to turn out to be expressions. So maybe parse S expression will be helpful for those things. Right? Okay. So that's kind of interesting. That tells us a lot about how we might want to structure this. Let's look at the list case first. So the argument was, not only does this have to be exactly 3 things long, but the first thing had better be an operator. Okay. So we can match the elements with, and we could say, well, this had better be 3 things long, where the first thing is an atom. And you can do this in OCaml. You can just write out a nested pattern, and it'll match on values that match this nested pattern. So I can say if it's an atom of some string, maybe we can check what that is in a minute, followed by some first nested expression, followed by some second nested expression, then we've got a chance of this turning into one of these real expressions, right? Because we're going to be able to do something with E1 and E2 to get expressions for them. And then we'll be able to figure out what the operator is at the beginning. Okay. What if this isn't the case? What if we have something other than an atom followed by 2 other expressions, right? What if we have something else? Anything other than this case? Yeah. The fail with? Okay. Other suggestions? Other suggestions? Yeah. Maybe there's some operations we can do on one expression. This comes down a little bit to how we define the language we're working over, right? If I say that the language is only 2 argument binary operators, then we're stuck. But you're right. Like maybe there's some cases where we define a slightly different language where you can do like minus on one argument and it negates it, right? Yeah. Maybe syntax error? Could you have expressions that evaluate to operators? So that would be, again, a decision about the syntax of the language. At the moment, I haven't really written down exactly what all the restrictions are on the syntax of the language that I have in mind. But I'm saying, for this, what I'm saying implicitly is it has to be an operator first, followed by 2 expressions. And so you said syntax error. So someone said fail with, and someone said syntax error, right? This is a case where we've looked at the structure of the string we got in, and it can't possibly look like a program we cared about. In some sense, I've answered your question and your question by writing down the data type of expr, right? Because I wrote down this abstract syntax data type for expr that only has numbers and operators defined as strings with 2 arguments. Right? So if I say our goal is to get to that expr data type, then we can't have these 1 argument things or these other expressions that evaluate to operators. Right? If we extended that data type to talk about more kinds of expressions, we could represent these 2 things. So we have a case where there's no choice in our representation of programs for how to take this string and turn it into one of those programs. There's nothing that matches. There's nothing that matches. This is like the soul of, the definition of when C or Java or any programming language says syntax error. Right? I was reading your program, I was reading the text of your program, and there is no way I can represent that as a C or a Java program. That's what Java C is telling you when it says syntax error. It's saying there's either a missing curly brace or you tried to do something that is not representable in Java syntax. There's no way I can go further with compiling this. This is not a Java program, or this is not a C program. In our case, if we have some structure here that doesn't have an atom followed by two potential other expressions, well, that's not a binary operator language program. It just can't be. There's not an operator followed by 2 expressions. It can't be. This is a syntax error. That is a syntax error. If we do have these 3 things matching, right, if we do actually have an atom followed by 2 expressions, then we know we must be trying to create one of these operators. So in this case, we could say we want to have an operator of whatever operator was provided, plus or minus. Now, there's definitely an extra check we could do here to make sure that OP is actually a string like plus or minus that we want to be representing an operator. I'm sort of skipping that and assuming it'll be plus or minus here, just for interest, in the interest of time. And then think for a minute. I don't want you to, don't shout it out to me. Think for a minute, talk to the person next to you. What should go in here? What should go in these 2 blanks? Because an op is going to take the string in these 2 things. Talk about this for a minute. What should go in here? What should go in these 2 blanks? Okay, all right. So the idea here, the key idea here, is that the 2nd and 3rd element of this list had better represent expressions. We had better be able to parse them as expressions in our expr data type. We'd better be able to get exprs for them. And that also matches what we expect to see in the 2 positions for op, right? We have better see exprs here. So in both of these places, we can recursively call parse sexp on the 2 corresponding expressions. And as long as those succeed and don't hit this syntax error case, we should get back 2 expressions that represent the nested expressions there. The last thing remaining is this base case for what to do when we have an atom, for what to do when we have just an atom here. What should we expect to see based on what we've written out so far? What kinds of strings should we expect to see for this to work out at the bottom for the atoms at the base cases? What should we expect to see? Yeah. Just numbers, right? We shouldn't expect to see like a plus or a minus here, because that would mean there's a plus or a minus as one of the 2 arguments, right? We only want to match the pluses and the minuses as this first thing here. So these had better all be numbers, right? So without trying to write out all the, there is a, so I'm going to say use int of string opt. So there's a function in OCaml called int of string opt that takes in a string and it'll give you back an int if it looks like an int with a sum wrapped around it using the option type, or it'll return none if it couldn't parse it as a string. And then you could report a parse error there. But the idea here is this would return num of some representation of getting the atom, which had better look like an int, into the num constructor. Okay. And then by putting together the built-in library function, it takes an S expression and takes a string and produces an S